Okay, we'll get started again. So we have just derived the kinetic energy in terms of the angular velocity vector omega and the angular momentum L. So if we now insert our expression for L here, we get this. Or in component form, the kinetic energy can be written in the following way. Now we can actually simplify this a bit further and write it in a way which is more convenient. If we introduce the axis of rotation. So let's say n is the vector which gives us the axis of rotation. And so that the angular velocity vector is given as the magnitude of it multiplied with n. By inserting this into the following equation and using that these are just scalars now. So they commute, meaning we can write the kinetic energy in the following way. I realize now I should have used a different symbol for the matrix. So let this underscore notation indicate that I is a matrix. And here, I is just a scalar. So by writing the kinetic energy in this way, we can relate T to 1/2 I omega squared, where I've introduced this quantity I. So this quantity I, should be under the bar here since it's a matrix, is given as the scalar product between the unit vector n and In, where I underline is the matrix of inertia. So you see then by defining I in this way, we obtain the kinetic energy in a quite familiar form. 1/2 of a quantity multiplied with the square of another quantity, which is remarkably similar to this well-known expression. So this allows us to sort of think of the kinetic energy associated with the rotational motion in an analogy of the kinetic energy of some linear motion, say. So you see here that this I plays the role of the mass, and the angular velocity plays the role of velocity. And whereas I underscore is the matrix of inertia, this quantity I, which is a scalar, is the moment of inertia around the axis of rotation. So I depends both on the composition of the rigid body, its mass density, its shape, due to the integration of the volume, in addition to which axis of rotation we're considering. So this means that a given rigid body will have different moments of inertia depending on the axis we are rotating it around. Some axes will have, for instance, smaller moments of inertia than others, depending on the symmetry of the body. And we'll have a look at this in just a little while. Now, let's consider some of the properties of this matrix of inertia, just as we did for the orthogonal transformations, to see if we can find some useful mathematical tools which helps us in the characterization of the motion of the body. So you see that the elements of the matrix of inertia satisfy this relation. If you consider its definition that we gave in terms of the integral of a rho of r and then r squared Kronecker delta minus this xj/xk. And in addition, we know that the elements of I have to be real. And these two facts in conjunction, namely that it's a symmetric matrix and the entries of the matrix have to be real, means that the matrix of inertia is an Hermitian matrix. And this is a term you might be familiar with from previous quantum mechanics courses, I guess, yeah. If we have a Hermitian matrix, do we know anything about its eigenvalues? Do you remember? So in quantum mechanics, physical quantities are represented by Hermitian operators, if you remember. Yeah.
Real?
They're real. So it means that the expectation value of some operator in quantum mechanics, which is Hermitian, has to have a real expectation value, which seems reasonable for a physical quantity. So we should always be able to diagonalize the matrix of inertia so that we can write the following. We should always be able to find a coordinate system where the matrix of inertia I underscore can be written in a diagonal way with real entries. So 0, 0 here just means that all these entries are 0. And in this particular coordinate system, these entries here have a special significance. Namely, they are the main moments of inertia for the body. Now, in some cases, it's more or less trivial to identify sort of the directions that give these main axes for the moments of inertia. If you have a highly symmetric body, for instance, like a top, you know a top? Like one of these things you spin and then it starts spinning. It has a special symmetry, which means that if you put one axis along just through the middle of it, that should be one main axis of moment of inertia. But for more complicated, arbitrary shaped rigid bodies, this tells us that we should still be able to find a coordinate system where we can diagonalize the matrix of inertia and identify these main moments of inertia.
Question: Is there always three main moments of inertia?
It's possible that one of them could be 0.
But it's maximum 3.
Maximum 3. Yeah. Yeah, for any 3D body.
Yeah.
So in this coordinate system, we have the main axis x1, x2, x3. And then precisely because this matrix of inertia is diagonal, both the angular momentum and the kinetic energy take a particularly appealing form. Because whereas in general, each component of the angular momentum will be a linear combination of all of these angular velocity components, since I is now diagonal, we have a direct proportionality between Li and omega I, where I is just a component along each of these main axes. So the angular momentum takes a very simple form in this special coordinate system. And the same thing goes for the kinetic energy, which now reduces to a simple sum here, instead of this matrix product, omega I omega. So I hope this convinces you that the coordinate system which diagonalizes the matrix of inertia is a very handy coordinate system to be working in, because it gives you very simple expressions for the angular momentum and the kinetic energy. Now keep in mind that regardless of which coordinate system you're considering, the angular momentum and the kinetic energy should be the same, right? The kinetic energy shouldn't depend on which coordinate system we consider. So we might as well just take the coordinate system which gives us the easiest expression, namely this one. So before we take the sample, consider the top, which I mentioned. let's say it looks something like this. In that case, if you have the third axis here, we said you have a symmetry in the plane, which should give you equal moments of inertia here, but they should be different from the third moment of inertia. If you have a completely spherical body, then all moments of inertia should be the same if it's homogeneous. I think before we take the example, I'll derive one thing, namely the Euler Equations. The Euler Equations we have encountered before, for instance, related to this brachistochrone problem, if you recall. So what we'll do now is to derive these Euler Equations in the context of rotation. The premise is the following. We want to find the equations of motion for the rotation of a rigid body around some fixed point. And this is what I meant when I initially stated that we're going to have a look at the quantitative description of how a rigid body now moves under rotation. So the aim is to derive some equations which we can solve analytically to find out exactly how the body rotates in space. Okay, so we'll start out by considering a situation where we have a stationary system with some observer, for instance us. And then we have the body, which corresponds to the rotating system. So we have that the time derivative of the angular momentum as seen from our observatory system is equal to the total torque, tau, exerted on the body. So this is valid in the stationary system. But we know that we can relate the time change of any vector in the rotating and the stationary system by means of the operator identity that we derived in the previous chapter. So we should have the following relation between the time derivative of the angular momentum in the stationary and the body system. So we have this extra term here. So as seen from the rotating system, we have the following equation of motion. I've just substituted the torque onto the left-hand side here. So dl dt now is implicitly assumed to be seen from the body, the rotating system. And tau is just a vector. So if it can be represented in the stationary system, we can always represent it in the rotating system as well. So this equation is valid in the rotating system. As an important limiting case, consider the scenario where there is no torque acting on the body. So we have a freely rotating system. Now, if we have a rotating system and we are positioned in the rotating system, we see that the angular momentum, as seen in the rotating system, will be conserved. We will experience no change in the angular momentum if the angular velocity vector is parallel to the angular momentum. But this is only valid in the case of a freely rotating system, so there is no external torque. Okay, so we know that this is valid in the rotating system, and at the same time, we know that the description of both angular momentum and kinetic energy is particularly simple in the special coordinate system where the matrix of inertia is diagonal. So in this system, we then have the main moments of inertia directed along the coordinate system's axis. Now this is just a component form of this, where I've written it out for each component. And so keep in mind that the cross product here is now represented by the Levi-Civita tensor. Now in this special coordinate system, we know that L can be represented like this. So if we insert these expressions for the angular momentum, we get the following set of equations. So you see now that these are differential equations with respect to time. And in general, they're nonlinear, actually, because we have this product between the omegas. But these are the equations of motion. So in a way you can think of them as sort of Lagrange, in the same way as Lagrange's equations, which give us equations of motion if you know the Lagrangian of the system. So then you have some differential equation which you have to solve, integrate in general, to find out how x, for instance, depends on time, the position. So in this way, we have to solve these differential equations to find out how omega, how the angular velocity vector, develops with time. And if we know omega as a function of t at all times, then we know exactly how the body rotates. So that is the aim. These are the equations of motion, and the aim is to find omega of t. And so we'll have a look at an example now. We'll consider free rotation of a rigid body, meaning that the torque exerted on the body is 0. And we'll show how this gives rise to a phenomenon known as precession. So now the goal is to use these equations of motion to find omega of t. And if we know omega of t, and we know how the body looks like, then we should be able to find both the kinetic energy and the angular momentum, because they're both related to the matrix of inertia and the angular velocity vector, only these two quantities. And so we'll find some kind of expression for these two quantities, but is there something we can say about them already now before having done any calculation? In other words, what can we say about the kinetic energy and the angular momentum for this situation? Exactly, they are conserved. And how did you reason to arrive at this conclusion?
We have forces on the system, and those quantities are generally conserved, but there are no forces and torques on the system.
Right, so L is conserved because we have no torque.
Yeah.
So the time derivative of L is equal to the torque. If the torque is 0, then the angular momentum is conserved. Now the kinetic energy, do you remember what the condition was to have conserved energy? It was?
Time-independent Lagrangian.
Yes. So as long as you have no explicit time-dependent forces or potential, or sort of injection or extraction of energy as a function of time, energy should be conserved. So just as you say, the kinetic energy and the angular momentum that we find better be constants, or we've done something wrong. Well, consider a somewhat simplified situation in terms of a specific symmetry for the body. So we'll consider a body which has a symmetry, meaning that two of the main moments of inertia are equal, like for the top spinning. So you have this symmetry in the plane, meaning that the two main moments of inertia in that plane has to be equal. But in general, there is then a third moment of main moment of inertia which can be unequal to these. If you now insert this into our equations of motion, things look a little bit better. We get this. So two of these equations are still non-linear, but this one looks pretty favorable. This we should be able to solve. So it follows that omega 3 has to be a constant. And the value of omega 3 will then be determined by the initial conditions that we choose. And if you now insert omega 3 here, we're back to a linear equation for each of them. In fact, we can write these two equations in the following way. By introducing this quantity large omega, like this, which is a constant because omega 3 we know is a constant due to this equation of motion. So by solving these equations, we can find this. You see that if I derive cosine, I get minus omega sine, which is equal to minus omega multiplied with omega 2. And similarly for this one. So we've basically achieved our aim. We have identified omega as a function of t. Where omega 3 is a constant. And this frequency is determined by the main moments of inertia and omega 3. You see that these are frequencies because they have dimension 1 over time. And so having arrived at our result, we now have to step back and look at it and say, what does this mean? How do we interpret this result? Well, let's say we have some rigid body like this, which satisfies this equation. You have the main moments of inertia in the plane being equal. Well, we see then that the angular velocity vector actually rotates with time, right? We have an x and y component, if you will, that go like cosine and sine. And so the angular velocity vector rotates in this circle around the constant omega 3. So I've just used I, j, and k for the unit vectors along 1, 2, 3 axis. So this vector here has a constant magnitude, since cosine squared plus sine squared is constant, and rotates around the system's axis number 3, or the z-axis, if you will. Now this is called precession. That you have this angular velocity vector that sort of precesses around some fixed axis. So this, the velocity with which the angular velocity vector rotates, is this omega. Right, so before we started, we could state that both the kinetic energy and the angular momentum have to be conserved quantities. So now it's time to check this. Since we are so fortunate to know the main moments of inertia, I1, 2, and 3, we know that kinetic energy expressed in this system is particularly simple. Namely, it has the following form. And so I've just used I1 here, since I1 is equal to I2, and we get this. So now we have to insert our solution for omega here and check if this is really a constant. And it turns out that it is, because this is just a squared, since cosine plus squared plus sine squared is 1. So the kinetic energy is indeed conserved. And in the same way, we can write down an expression for L, or L squared. Like this, where I've again used that cosine squared plus sine squared is 1. And so this is also a constant. So that looks good. And well, we applied this to a body which has a specific symmetry, right? It looks slightly different in the third direction, the z direction, as compared to the plane. Do we know of any body that looks somewhat like that? A large body? Earth. To a very crude approximation, of course, but still. Because Earth is slightly squished at the poles. Yeah, so this is supposed to represent a situation where we have this symmetry in the plane. In which case, the main moment of inertia along the z-axis here, we have a north pole and south pole, is larger than the moment of inertia in this plane. So according to this analysis, the Earth should in fact precess. The frequency with which it should precess is given by this expression for omega. Omega 3 here, sorry. And you can actually calculate these values for the main moments of inertia by using some model for what the Earth looks like. And what you come out with is that this large omega is about 1/300 multiplied with omega 3. And omega 3, in the case where this body is the Earth, has a well-known value to us. What value would you say omega 3 has for Earth? Or if you will, the period associated with omega 3. Mm-hmm.
1 day.
1 day. Because omega 3 represents the rotation around the third axis, and as we know, the Earth spins around its own axis in 1 day. So T3 here, which is equal to 2 pi over omega 3, is 1 day. Which means that the period of precession should be about 300 days. So it's a quite small effect, but it's still there if we can neglect any external torques acting on the Earth. And yeah, let me write that. One has actually measured this effect, and what one came up with was 440 days. So that's a pretty large deviation, about 50%. But I guess we have to attribute that to the fact that this is a highly idealized model for Earth. So, and also, Earth isn't a perfectly rigid body either. We have oceans, we have magma inside the Earth, etc. But okay, 300 days for 440 days, roughly the same ballpark at least. So this is a real effect. Okay. See you tomorrow, hopefully.